everyone, welcome to GATE Academy. This is Richa Gupta with you all, and I'll be dealing with the quick revision for open channel flow. So my dear students, as you are preparing for GATE and in the very last month of GATE, or basically when you are clear with your subject, so here I am with you with a quick revision of open channel flow, so that you can brush up all the things which you have studied, or you can say you can quickly revise the things, the formulas which are necessary or which will be helpful in solving your problems, right? So here we will proceed with a quick revision of open channel flow as follows. Now, open channel flow, we will start from the definition part, because open channel flow in short is known as OCF. So now, what is this open channel flow? It is the flow where the liquid flows through any channel with a free surface subjected to atmospheric pressure, right? Now, two things which we have to keep in mind is liquid, it can be any liquid, but in the problems basically we deal with water. Now, through any channel, yes, be it alluvial channel, be it a narrow channel, wide channel, any channel, be it a channel having lot of turbulence or a channel which is flowing very slowly, very mildly, very calmly, then also, right? So this will be your definition for open channel flow. But the condition for a channel to be open channel is that this free surface, it should be subjected to either atmospheric pressure, fine, or it should have a channel which is exposed, which should have a free surface, right? Now, moving to the second thing, that is your head. What is head? Head is the energy per unit weight of fluid with respect to data. And if you go through the expression part, it is the summation of your potential head plus pressure head plus kinetic head. If you want, I can draw the diagram also to show you. If this is some slope, so this is your Z, this is your Y, and this is your V square by 2G. This line is known as your total energy line. In short, we write it as TEL, and this is known as your hydraulic gradient line, and this portion is your data, right? So it is the sum of what? Z is also known as your datum head. This is your pressure head, that comes out to be P upon gamma, that is P upon rho G, or you can say it P upon small w, and V square by 2G. Fine, that is your kinetic head. Now, moving further is the definition of your steady flow. We will just do faster the steady flow, uniform flow, because this is something which is very preliminary and is clear to you, right? So now, moving to the steady flow, flow parameters at a particular section of channel reach are constant with respect to time. That is, if you go through the expression format, del V by del T is equal to 0, del Q by del T is equal to 0, del Y by del T is equal to 0. Now, similarly, unsteady flow, just the opposite of steady flow, that is, flow parameters at a particular section of channel reach varies with respect to time. In the steady, it was not varying, while in the case of unsteady, it will vary, right? Now, in this expression, del V by del T is not equal to 0, del Q by del T is not equal to 0, and del Y by del T is not equal to 0, where Q is your discharge, V is your velocity, Y is your depth of flow. Now, similarly, we will come to the uniform flow. Just one thing more. When you are dealing with steady flow, all the parameters with respect to time, fine, and when you will be dealing with uniform and non-uniform, all parameters with respect to space, fine, don't confuse with it. Uniform flow, flow parameters at a particular section of channel does not varies with respect to space. That is, you can say is constant also. That is del V by del X. Here we are taking del X, remember, and in the study we were taking del T, right? So del V by del X is equal to 0, del Q by del X is equal to 0, and del Y by del X is equal to 0. Similarly, to the non-uniform flow, if we will go, flow parameters at a particular section of channel varies with respect to space. That is what we can say, del V by del X is not equal to 0 since it is varying, fine. The thing, when it varies, you won't have the differentiation, that is the differentiation of velocity with respect to space won't be constant, fine. Now, we will have the combination of flows for these different types, that is steady, unsteady, uniform and non-uniform. So, we have just the permutation combinations of the various types of flow. First, steady uniform, steady non-uniform, unsteady uniform and unsteady non-uniform. Now, just 1 second I will take just to explain you that out of these 4 flows, if you will see, theoretically all the 4 flows are possible. You just have to substitute the definition of steady flow and uniform flow. Flow parameters are constant with respect to time, with respect to space. Flow parameters are constant with respect to time but varies with respect to space. Flow parameters varies with respect to space but is constant, varies with respect to time but is constant with respect to space. Last one, flow parameters varies both with respect to time and with respect to space. So, what you see out of this all the 4, unsteady uniform flow is practically not possible. It is practically not possible, right? This is one thing which you should know. Fine. Now, you are clear with this whole part, all the introductory part here we dealt. This was just the preliminary introduction part. Now, moving little further, little higher things, that is your wetted perimeter. What is your wetted perimeter? Length of the boundary of the channel in contact with water. That is, if this is your rectangular channel section, this is the width B, then what you will have? You will have the wetted perimeter as B plus this Y, and here also you will have a Y, because it is the length of the boundary. This is the whole boundary of the channel in contact with water, right? So, this is your wetted perimeter. You denote it by P. Now, if you have a wetted perimeter, you will have a wetted area also. So, this is wetted area denoted by A. What else is known as area, which is wetted by the channel. That is, if you see the rectangular channel section only, your wetted area will be width into the depth of flow, right? Now, moving further, hydraulic radius, which is very important when you will go to the numerical part of the open channel flow. So, it is simple, it is the ratio of your wetted area by wetted perimeter, and if anyone asks you regarding the units, you can say that it can be in meters, because area will be in meter square, perimeter in area. So, you will get the hydraulic radius in meter. You have that small misconception that whenever we are talking about a ratio, you generally what you do is you think that it is dimensionless. So, it is not like that, fine. Now, moving to the hydraulic depth, this is very important, I will tell you when. Hydraulic depth is the ratio of your wetted area to that of the top width of the channel, fine. If you get top width of the channel section in contact with water, this is the top width, this is this portion, the channel section which is in contact with water, the top width of that portion, fine. Now, moving to further, that is depth of flow, which you denoted by Y, and there is another, that is depth of flow section, which you denoted by YN, right. Now, what is the difference between the two? When you are talking regarding the depth of flow, it is the vertical distance measured from channel bottom to top surface of water. While if you are talking regarding depth of flow section, it is the normal distance which is measured from the channel bottom to top surface of water. Fine. The reason I am telling you is, sometimes in the question they will give you depth of flow and sometimes they will give you depth of flow section. So, you should be able to decide whether it has given you Y or it has given you YN, that is the normal depth, right. Now, moving further is the various types of flow. How could you know that whether a flow is your laminar flow, transitional flow or turbulent flow? I haven't written the definition of laminar, transitional, turbulent. I know that you are very well acquainted with it. Fine. Just for now, I will tell you the definition. Laminar, when the water moves in layers or when the fluid moves in layers, fine, streamlines are parallel. In case of turbulent, all the things which happens in laminar flow, just the opposite, water moves in a haphazard manner, there are high undulations, streamlines are not parallel and there is a lot of turbulence, and transitional is somewhere between laminar and turbulent, not moving in layers but also not having a lot of turbulence as well, right. So, if I want to classify a flow to be laminar, transitional or turbulent, I need to calculate first the Reynolds number. If you go by the definition of Reynolds number, it is what? It is the ratio of your inertia force to that of the viscous force, right. So, we denote it by Re, and now if there is a pipe flow, the reason I have to compare between the pipe flow and open channel flow, first I will tell you that. The reason is, in the case of classification for laminar, transitional or turbulent, pipe flow has some different criteria, while in the case of open channel flow, the Reynolds number criteria is different. So, please do not get confused, that is why I have written both the things here, right. So, laminar pipe flow Reynolds number should be less than 2000, for transitional 2000 to 4000, and for turbulent greater than 4000. Similarly, if you will go laminar in open channel flow, it is less than 500, and for transitional it is 500 to 2000, and if it is turbulent it is greater than 2000, right. And if you are told to calculate Reynolds number, I will write it here. Reynolds number Re is given by rho VL by mu, fine. Basically, this LC is the characteristics length, fine. This varies, like it is equal to the diameter in the case of your pipe flow, fine. So, you can see that Re, that is your Reynolds number, is equal to rho VL, that is LC is your characteristic length, divided by mu, that is your dynamic viscosity, fine. You can also write it as VLC by mu, because mu by rho will give you kinematic viscosity, right. This you would have studied in your FM, that is why I have not written it. Now, Froude number, which is very important, because as for now, when you will go basically to the rapidly varied flow, you will have these terms, and especially when you will go to the hum cases, which we will be dealing further, then you will realize the value of Froude number in open channel flow, right. So, now what is Froude number? It is an index of classification for the different types of flow. Like whenever I want to say that something is greater, something is lesser, then there should be an index of classification, that with respect to this, if it happens, so it is this. With respect to this, if that happens, so it is that. Fine. Similarly, Froude number is an index of classification for the different types of flow in open channel. And if you go through the expression format, this Froude number is equal to V root over GD. Now, what is this V? I will tell you, this is velocity, G is acceleration due to gravity, and if you go through this D, this is your hydraulic depth. Now, you get the reason why I was to tell you the geometric parameters, because maximum cases I will tell you, they ask in the questions regarding the rectangular channel. So, you would have the habit of substituting Fr is equal to V root over Gy. This is right, but only in the case of rectangular channel section, while for the other shapes of the channel section, be it trapezoidal, triangular, any shape, you have to calculate the hydraulic depth. Fine. Now, what is Froude number? Froude number, if it is greater than 1, it will be a supercritical flow. If it is equal to 1, it will be your critical flow, and if your Froude number is less than 1, then it will be a subcritical flow, right. So, this you should remember, this is important. One thing more, you will have a critical depth also, YC. YC will be your critical depth. The reason I am telling you here, I thought I will tell you in the energy depth relationship, but I will tell you here also. When your given depth is less than your critical depth, then it is for the supercritical flow. When your given depth is equal to the critical depth, this is your critical flow. And when your given depth is greater than your critical depth, this is the case of subcritical flow. Reason I am telling you here, what the students thinks I do not know, but they do it. Fr greater than 1, Y should be greater than Yc. No, my dear students. When your Froude number is greater than 1, your given depth would be less than your critical depth, because here if you let us say go with the rectangular channel. So what you see that here the value should be less than the critical depth, then only you will get the value higher than the given Froude number for critical flow, right. So I hope this is clear to you. We will move further. Then we come to the velocity distribution. What is velocity distribution? We have to calculate the average velocity in open channel flow. So you can calculate it in two manners. First is V average is equal to V.6. What does this V.6 means? Velocity at a depth of 0.6 y0 from the free surface, right. Now there is another more reliable method of calculating by taking the velocity at a depth of 0.2 y0 and at a depth of 0.8 y0 and dividing it by 2. Fine. So we can write it velocity at a depth of 0.2 y0 from the free surface, then velocity at a depth of 0.8 y0 from the free surface. So this second one is more reliable as compared to the first. Now moving to the average velocity generally it has not been asked, but still I have written it, this portion. Average velocity is equal to 1 by A root over V dA. This is the elemental area, elemental velocity. Fine. Then we will be dealing with the kinetic energy correction factor, which you denoted by alpha. Reason I have told you here, because when we will be dealing further in the quick revisions regarding the assumptions of gradually varied flow, there this alpha will come into practice, that kinetic energy correction factor alpha is unity. So that's why I wanted that you should know alpha. And if you want to listen definition with me, so basically alpha, it is the ratio of actual kinetic energies per second. Basically you can say it is the ratio of kinetic energy of flow per second based on actual velocity to the kinetic energy of flow per second based on average velocity. So here is the expression format of your kinetic energy correction factor. This alpha is also known as by Coriolis coefficient also, right. Now momentum correction factor, I have written the expression. If you go to the definition, it is the ratio of momentum of flow per second based on actual velocity to the momentum of flow per second based on average velocity. Fine. So this is also known as beta, is also known as Bosniak's correction factor, right. So I hope this portion is clear to you. Now we will move towards the uniform flow. So now for the uniform flow we will start. What is uniform flow? I told you earlier also. A flow in channel is said to be uniform if its properties, that is the flow parameters, are constant with respect to distance. This we have already studied. So now I have drawn this diagram for you. There are two sections, name it section 1 and section 2, separated by a distance L. Now if you apply Bernoulli's equation at section 1 and at section 2, you will get this end results. Fine. You will get basically Z1 is equal to Z2 plus head loss. So you will divide it by L, you will get the slope, that is Z1 minus Z2 divided by L. And I have written here V1 is equal to V2, Y1 is equal to Y2, because you know that flow parameters are constant at a particular section, right. So now this is the formula for your average shear stress on the wetted perimeter tau naught, and it is given by gamma Rs, where R is your hydraulic radius and S is your bed slope. You can also write it by S naught or SB, whatever denotation you want, right. Now third one is your Chase's equation, and it is given by V is equal to C root over Rs. And why we use Chase's equation? We use it to calculate the velocity, right. And what is C here? It is Chase's coefficient. So Chase's coefficient, in case you haven't been given, but you have been given the value of friction factor, you can write it root over 8G by F and you can calculate Chase's coefficient, right. R is hydraulic radius, S is bed slope only. Now what happens is, although this equation haven't been asked till now, but I am just telling you for your purpose only, that this C is Chase's coefficient, right. you can derive it by root 8g by f. What else you can do is, there are other people who have given the formulas, like Gangold Cutter's formula is given to us to calculate the Chase's coefficient. So this is the formula where n is your roughness coefficient. Fine, this is one of the formula. This is Bazin's formula for calculating the Chase's coefficient. This value of m, if it is asking you to calculate the Chase's coefficient with respect to Bazin's formula, this m depends upon the type of surface. Fine, so generally this value will be given to you, but till now it hasn't been asked, right? Now, moving to the important formula which has been used many a time in your open channel flow is your Manning's formula. It is given by 1 by n r to the power 2 by 3 s naught to the power 1 by 2. Fine, n is Manning's roughness coefficient. Fine, or you can say constant. Now, what is the relation between your Chase's constant coefficient c and Manning's roughness coefficient n? This is the relation. C is equal to 1 by n r to the power 1 by 6. In case they would be giving you Manning's roughness coefficient and they'll ask you to calculate velocity by Chase's formula, you can calculate Chase's coefficient and you can substitute it, provided you should know this relation, right? Now, what else, like we have been given the values, the formulas for knowing the value of C. This value of C, for knowing it you have been given two formulas. Similarly, for this constant Manning's roughness coefficient, for getting this value, basically Strickler's equation is used, and if you remember previous years 2004 I guess, in that question related to Strickler equation has been asked, right? So, n, that is Manning's roughness coefficient, is equal to k to the power 1 by 6 divided by 24 or d50 to the power 1 by 6 divided by 24. And since, just remember one thing, it is an empirical equation, because of which this k value, which is the roughness height, or if you are substituting d50, fine, this has to be in meter. Otherwise, you can't use this formula for calculating Manning's roughness coefficient, right? So, you should remember this. Fine. Now, we have to do it quickly. Ninth one is your Mayer's formula. When your bed particle size, that through which 90% of the bed material will pass, coarser soil is there, then you use, this is the Mayer's formula, that is n is equal to d90 to the power 1 by 6 divided by 26, right? Last one is your conveyance. What happens if in the question, instead of giving you the value of V is equal to 1 by n r to the power 2 by 3 s to the power 1 by 2, but they will ask you discharge and some values they will give, something like that they will do, or instead of giving all the values they will give you the value of conveyance. So, how could you know the other values? Conveyance is equal to 1 by n a r to the power 2 by 3. Right? Hope you are clear with this. We will move quickly. Now, most economical or most efficient section of channel. This topic is important as per your gate examination. So, now, what is first of all the most efficient or most economical channel section? A channel is considered to be most efficient or most economical when it can pass maximum discharge for a given cross sectional area, for a resistance coefficient n and bottom slope. That means when your A, that is area, cross sectional area, resistance coefficient means n and bottom slope means s. If these three are constant and you want to get the maximum discharge, then we say that your channel section is most efficient or most economical, right? One more thing in this is your perimeter should be minimum. Fine, because when your perimeter will be minimum, your construction cost will be less, right? So, now for rectangular channel section, this is a rectangular channel section. If it is the most efficient and most economical channel section, rectangular channel section, then your this width will be equal to twice the depth of flow. One thing. Your hydraulic radius, which is the ratio of wetted area by wetted perimeter, will be equal to y by 2, right? And on other things I have written, that is top width is equal to 2 into depth of flow, perimeter is 4 into depth of flow, and your hydraulic depth is equal to depth of flow. the thing you should remember is this one and this one. If you remember these two things, because that is I have marked it in block, then it is more than sufficient. These all things you can derive, right? Now, moving to the trapezoidal channel section, whatever things I have marked it in block, that is important for you. Other things, if you are clear with the concepts, you can derive it. Fine. Now, trapezoidal channel section, here a trapezoidal channel section is drawn, and what you see, this is basically a definition also, basically you can say a statement, that will be more prevalent, a statement. And what does this say? Half of top width. What is the top width? B plus my plus my, that is B plus 2my. So, half of top width is equal to the length of the side slope, or you can say the slant length. This is your y root over 1 plus m square, and this is your depth y, right. So, half of top width is equal to the slant length in case of your most efficient or most economical trapezoidal channel section, right. This you should remember it, because sometimes they give statement wise questions also. The second thing which you should remember is that hydraulic radius is equal to half the depth of flow. The other thing is m is equal to cot 60, or you can say m is equal to 1 by root 3. This is important, because if you know the value of m here, you can calculate b is equal to 2 by root 3. And similarly, all other parameters, that is p is equal to 6y by root 3, that is perimeter, hydraulic depth is equal to 3 by 4y, top width is equal to 4y by root 3. And what is the area? Area is root 3y square, right. So, all other parameters you can calculate. If you are good in memorizing, you can memorize this also, no problem. But the things which I have marked it in block, that is more than sufficient, or you can say, and it is more important, right. Now, moving to the triangular channel section, right, and here you can see a triangular channel section, side slope is 1:m. Now, if it is a most efficient one, your theta will be 45 degree, and the total angle you can say it will be 90 degree, right. Your r, hydraulic radius, will be y upon 2 root 2, fine. This you should remember, that is theta is 45 degree and r is equal to y upon 2 root 2, right. Top width is 2y, area is y square, perimeter is 2 root 2y, and d is y by 2, that is hydraulic depth is half the depth of flow, right. One thing which you can get common is hydraulic radius r is same for rectangular channel section and trapezoidal channel section. And one more statement which I haven't written in trapezoidal channel section, it is when your theta is 60 degree, your internal angle, like when your theta is 60 degree here, fine, here you will get an internal angle 120 degree, this will be also 120 degree. So, the most efficient trapezoidal channel section is half of regular hexagon. What I said, most efficient trapezoidal channel section when your theta is 60 degree side slope angle and the internal angles are 120 degree. So, you can say it is the most efficient trapezoidal channel section is half of regular hexagon. One thing more which is there is this B, the width will be equal to the slant length, that is B will be equal to L, and this angles will be 120 degree. That then only you can say that it is half of regular hexagon, right. So, this was one of the things, because I think in statement wise if they ask you regarding the most efficient or trapezoidal channel section, you will be able to mark the questions right, fine. So, this we have done regarding the uniform flow. Now, we will move regarding the energy depth relationship. So, now after uniform flow, we will be talking regarding the energy depth relationship. All the things which are important, which are necessary for solving the questions or which are helpful, which help in solving the questions regarding the concepts, regarding the formulas, we will be discussing it here, right. So, now first of all, we will start from the basic. I know you would be knowing it, but still, right. So, that we could have that scenario that okay, we are starting from the basics and then we are proceeding it further, right. So, now specific energy, what it is the total energy at a section with respect to channel bottom as datum. How come? Just look at this figure. This figure you would have already seen. Here you have your Z datum head, Y depth of flow, and your kinetic head, or you call it as your velocity head. So what is this? This is your total energy line. You can call it as energy line slope. This is water surface slope, and this is your channel bottom. Fine. Now, if you take this channel bottom as datum, you will get this specific energy E. You denote specific energy by E, which is the summation of, or you can say it includes, the depth of flow Y and velocity head. You can call velocity head as kinetic head also. Now, I have written this E is equal to Y plus V square by 2G. This is valid for any shape of the channel because this is simply the specific energy. Now, I have written here for rectangular channel, your E, that is specific energy, is equal to Y plus Q square upon 2G Y square, right? This is the rectangular channel specific energy. You can denote it in this way also and this way also. Now, if you have query just for once that how it came, I will tell you. That is, discharge is equal to area into velocity, right? Now, what is area for rectangular channel section? That is width into the depth of flow, right? This I am doing it quickly because you know this. Now, what is Q divided by B? That will be your discharge per unit width, which will be equal to Vy. That is velocity into depth of flow. So, now in place of velocity, you substituted discharge per unit width divided by the depth of flow, and you got this relation, right? Now, we will plot the graph corresponding to the specific energy and depth of flow. This is the resultant, this one which I have marked in this curve shape. This is the resultant which you get, right? So, now what is happening? There is x axis where you are plotting specific energy. There is a y axis where you are plotting the depth of flow. Now, I will plot any specific energy E1. I will plot any specific energy E1 corresponding to which I will get two depth of flow. As you can see in the graph, I have marked it in dots. I will bold it more if you want. So, you can see that corresponding to a particular specific energy, there are two depth of flow. One is Y1, one is Y2 because it is touching at 2 points on the curve. So, what happens? You will see that for any particular specific energy, there are two possible depth of flow. This is Y1 and Y2. But obviously, there will be a term which is used for the depths which have the same specific energy, right? So, the depth which have the same specific energy, they are known as your alternate depth, right? Just one thing more, after this when we will be studying rapidly varied flow, you will be having the conjugate depth and sequent depth into picture. So, do not get confused that what happens in alternate depth, what happens in conjugate or sequent depth. I will tell you here only that in the case of alternate depth, you can see that specific energy is same, while in the case of your sequent or conjugate depth, your specific force is same, right? So, now this much is clear what is alternate depth. Now comes what I have written here, E minimum, you call it as minimum specific energy, or you can say EC, which is the critical specific energy. So, what happens is, although if you plotted any specific energy on the right side or you plot it to the left side, you will be getting two depths of flow, but there will be one specific energy corresponding to which you will get only one depth of flow. So, that specific energy is known as E minimum, or you can denote it by EC, right? And the depth corresponding to it is YC, that is your critical depth. Fine, this much is clear. So, I have written this, but I wanted that this should be clear to you. Instead of marking what is alternate, conjugate or sequent depth, you should be clear with the concepts. So, now for a given specific energy, there are two possible depths, y1 and y2, known as alternate depth. At minimum specific energy, there exists only one depth of flow known as critical depth of flow. This much is clear? Now, this was regarding the conceptual part. Now, there are some formulas which are helpful in solving your numericals questions. Although you can derive it, but why to waste time when you have the formulas, right? So, now critical depth, if it is given in the question to calculate the critical depth, because such type of questions have already been asked. So, for rectangular channel, your critical depth Yc is equal to q square g to the power 1 by 3. This small q is discharge per unit width, right? Now, for triangular channel section, your Yc is 2q square upon gm square to the power 1 by 5. Fine, here you are having discharge, and in the case of rectangular you are having discharge per unit width, right? So, this is your triangular channel. What is m if you want? This, when you were drawing a triangular channel section, something like this. This was your triangular channel section. So, you have side slope in the ratio 1:m. Yes, we were taking in the derivations and all. So, 1:m. So, this m is that only, right? Now, minimum specific energy, if you are asked in the question to calculate the minimum specific energy, following are the formulas for various shapes of the channel section for which you can calculate the minimum specific energy, right? So, now in the case of rectangular channel section, E minimum is 3 by 2 by C, that is your critical depth. I will tell you how it comes, just the basics, like you know that E is equal to y plus v square by 2g, this I told you, right? When your E becomes E minimum, that is what is happening, your E becomes E minimum, then what will happen, y becomes yc, E becomes vc, right? This much is clear. Now, what is happening is, if you want to get this 3 by 2 yc, I am going through this one, what you will derive it, if yc is yc by 2, then you will get 3 by 2 yc. Obviously, that means your velocity head, or you can say that the kinetic head is equal to half the depth of flow in case of rectangular channel, right? Now, moving to the parabolic channel, you have E minimum is equal to 4 by 3 yc, that is yc plus yc by 3. So, what you can say, that your kinetic head is 1 by 3 times or 1 by 3rd of your depth of flow, right? Now, moving to your triangular channel. Triangular channel is E minimum is equal to 5 by 4 yc, that is you can write it as yc plus yc by 4. So, 1 by 4 times depth of flow is equal to what? Your velocity head, right? This much is clear. Remember this is very simple, solve 2-3 questions, the formula will be remembered to you automatically, right? Now, condition for critical flow for any shape of the channel, be it rectangular, triangular, trapezoidal, circular, any shape of the channel, be it parabolic or exponential also. You have this relation q squared t upon ga cube is equal to 1 as true. You could have written this formula as q square by g is equal to a cube by t. In this format also you can remember, or in this format, that is q squared t upon ga cube is equal to 1. This is the condition for critical flow for any shape of the channel, right? Now, the most important part, or one of the most important thing which have been asked in the gate and which has carried so much of concepts with it, right? That is the channel transition. So, in channel transition, broadly we will be dealing with two different types of channel transition. One is your channel with a hump, and second one is your width contraction, or you can say contraction of width or width reduction, anything you can say, right? So now, what happens channel with a hump case? Here I am talking regarding the raising of bed. Fine, that is hump introduction, the bed has been raised. I am not talking regarding the lowering of bed. Remember that, fine. Now, channel with a hump, first case, that is your subcritical. Just one thing, in the case of your subcritical, your depth at section 1 is always greater than the depth at section 2. So, I have written already y1 is greater than y2, right. Now, what happens is, first I can see that E1 is the specific energy at section 1, E2 is the specific energy at section 2. So, how could I write it that this E1, this particular E1 is equal to what? This E2 portion plus your delta Z. Delta Z is any, I do not know the value, I am just telling you delta Z is the height of the hump, fine. This is the expression. E1, you can see it clearly from the figure. E1 is equal to E2 plus delta Z, right. Now, I am saying that I want to increase the height of the hump. I do not know, but I want to increase the height of the hump. I want this delta Z, that I want to increase this up to a maximum limit. So, what will happen? In the case when your delta Z, that is the height of the hump, is equal to your maximum height of the hump, your energy at section 2, that is E2, changes to EC, that is critical specific energy. So, what we will get? E1 will remain E1, E2 will change to EC and delta Z will change to delta Z maximum. This much is clear? This is important. The reason I will tell you, what happens in the question, sometimes they ask you, what is the maximum height of the hump which is possible for the given flow conditions without changing the upstream flow condition. So, what will happen in that case? Your E1 is E1 only, that means your upstream condition is not changing, but your E2 changes to EC and your delta Z changes to delta Z maximum. Just one thing more, when your E2 changes to EC, what is happening? You know what? If you plot the graph specific energy curve, you will see that y1 and y2, both the values are greater than your critical depth. Just one thing, you can look at this figure. You know that any value greater than yc, this is the subcritical zone and this is your supercritical zone. So, what happens is, these two values are y1 and y2 in the case of subcritical are greater than your critical depth. So, what will be happening is, your y2 value will change to yc, that is y2 decreases to yc, fine. So, this was happening, E2 was changing to EC. Now, what is happening? I am telling no, I want to increase the height of the hump above the maximum height of the hump. So, what will happen? This flow won't be possible. I have to change the flow conditions. So, what will happen? The flow conditions will change, that is your E1 will change to E1 dash, fine. Your section 2 flow will remain critical. I will tell you how. When you increase the height of the hump, let us suppose delta Z dash, which is greater than delta Z maximum. Denotion does not matter, you can use your own denotions, you can use instead of delta Z, you can use delta X, anything. This expression format should be clear to you, right. So, when you are increasing the height of the hump delta Z dash, which is greater than delta Z maximum, what will be happening? Your EC, which was there, your specific energy at section 2 will be less than the critical specific energy, and for a flow to be possible for subcritical, your minimum specific energy should be EC or E minimum, but if your specific energy is less than the given critical specific energy and your height of the hump is greater than the maximum height of the hump, then it is the choked condition. This condition is your choked condition. That means flow will not be possible with the given conditions, and what will happen for the flow to be possible at downstream condition, section 2 will remain critical, that is EC, but flow at upstream changes to E1 dash, E changes to E1 dash, and your depth of flow Y1 changes to Y1 dash, right. So, I have written here upstream flow condition is changed from E1 to E1 dash, that is depth of flow increased from Y1 to Y1 dash, depth at section 2 remains critical. So, everything will be same, E1 will change to E1 dash, Y1 dash will be greater than Y1 and your section 2 will remain critical, right. So, now similarly supercritical flow, many things are same for subcritical and supercritical, changes will be only somewhere between. I will tell you what. Here your Y1 was greater than your Y2, here it will be opposite, that is your upstream depth Y1 is less than Y2. I have written it here, Y1 is less than Y2. Now everything what was going on here, it will be same for supercritical also, that is you can see E1 is equal to E2 plus delta Z. So, E1 is equal to E2 plus delta Z. Now, when I was increasing delta Z to maximum, what was happening? E2 was changing to EC and delta Z was changing to delta Z maximum. This is also same. Even when you are increasing the height of the hump greater than the maximum height of the hump, this condition is also same. Then what is the changes? Specific energy increases, right, but the depth corresponding to the new specific energy, that is Y1 dash at section 1 will be less than your given depth Y1 initially. That is the change. So, I have written the upstream flow condition is increased from E1 to E1 dash, while the depth of flow decreases at upstream end, that is Y1 dash is less than Y1. In this case what was happening? Y1 dash was greater than Y1 and here Y1 dash is less than Y1, right. Now moving to the width contraction, here also two cases which we will be studying, that is a subcritical and supercritical case, right. So, first moving to the subcritical, same thing, your depth at section 1 will be greater as compared to the depth at section 2. Let B1 be the width at section 1, B2 will be the width at section 2. There is no case of hump, only exclusively we are focusing on width contraction, right. So, now you know that discharge per unit width is equal to discharge upon width. So, if your width is greater, because it is in the denominator, your discharge per unit width will be what? Lesser. So, similar thing is happening, quickly we will do this. If your B1 is greater than B2, obviously your Q1 is less than Q2 because B is in the denominator, right. Now, what I am planning? I want to reduce the width. At section 2, I want to reduce the width from B2. I will reduce it, I can reduce it up to B minimum, that is the minimum width which is possible for the given specific energy. That is your E1 specific energy at section 1 is equal to E2, that is the specific energy at section 2, which is equal to EC, that is the critical specific energy. So, all these three conditions are satisfied, that is in this case your QC, that is discharge per unit width, is equal to Q upon B minimum, that is the minimum width which is possible without changing any upstream or downstream conditions. This condition will hold true, and if they will ever ask you what is B minimum in the question, so QC is equal to Q upon B minimum, and this is the expression. Now, if you are telling no, a minimum width which was possible, I want to reduce it below it also, I want to reduce it further, okay fine, you can do. But what will happen? Flow will occur, basically it will occur, for no problem, for sure it will occur, but not with the given conditions which was happening initially. That is, I have written here Q3 is greater than QC, flow is not possible with the given specific energy, because what will happen? If your width is less than your minimum width, your discharge per unit width will be greater than your critical discharge per unit width. So what will happen? Now conditions will change. Again upstream condition will change from E1 to E1 dash. Your Y1 dash will be greater as compared to your Y1, but in the case of your hump, nowhere your section 2 remains to be critical. But in the case of hump, although your section 2 remains to be critical, but the critical depth changes in the case of width contraction. That is, if it was Y in YC initially, it will change to YC dash and the critical energy will be EC dash. So this is only I have written. If B3 is less than B minimum, upstream condition will change. Y1 dash is greater than Y1, new specific energy E1 dash is greater than E1, flow at section 2 remains to be critical, but a new critical depth YC dash will be formed such that YC dash is greater than YC, right. So all the things which I have written, it is in the expression format. E1 dash is greater than E1, EC dash is greater than EC. So what will happen? For subcritical, Y1 dash will be greater than Y1, YC dash will be greater than YC. But what is the changes? You can see that E1 dash will be equal to EC dash. In the initial cases, E1 was equal to E2 was equal to EC. For the same specific energy, you were having all this. But when you reduce the width below the minimum width, you got E1 dash is equal to EC dash. Now, for supercritical, everything will be same, only the same changes. Y1, that is depth at upstream, will be less than depth at downstream. And your E1 dash will be greater than E1 in the case this condition will hold true initially. I haven't written because it will be same thing, I am repeating it again. I am telling you, this should be understood to you. This condition will be same. Up till this QC is equal to Q minimum, everything was going same. Now what will happen is, you will see that if you are reducing the width below the minimum width, here also your upstream flow condition will change, specific energy will increase from E1 dash to E1, from E to E1 dash, sorry, your specific energy will increase, your critical depth will also increase, EC dash will increase, EC will increase to EC dash basically. Fine. So what you will get it, obviously when your EC dash is increasing, your YC dash is increasing, but just one thing which is different is, your E1 dash is increasing, but your Y1 dash corresponding to E1 dash is less as compared to your initial depth of flow at section 1, that is Y1. This is the only change. So here also E1 dash will be equal to EC dash, right. So I hope this is clear to you. Just one thing, if you have query, why in the case of supercritical Y1 dash is less than Y1, so you can plot. Let us suppose if any E1 dash, so let us suppose this is your E1 dash, and if I want to see it in the subcritical zone, so this, if you see it, you will see yourself that this is Y1 dash, this is somewhere here. So what you see, E1 dash is greater than E1, but here Y1 dash is less than Y1 for the same specific energy. And if I extend it upwards, let me extend it upwards. So what you will see, you will have an energy, if here it was Y1, fine, now I am considering this region. If here it was Y1, the depth would have been Y1 dash. Fine. So that's why I told you that with the help of graph, you can get the answer for all your queries, that why Y1 dash is less than Y1 in the case of supercritical and Y1 dash is greater than Y1 in the case of subcritical, right. So I hope this energy depth relationship clear, although I know that there will be was slight slow I was, but I wanted that these concepts should be clear to you, right. So now we will be moving to the gradually varied flow. So now, after energy depth relationship, we are moving to our gradually varied flow. So we will be starting with the definition part of the gradually varied flow first, then we will be moving further towards the expression format of it. What is gradually varied flow? What we called it? It is a basically steady non-uniform flow where the depth of flow changes gradually over the length of the channel. That is, if I will draw a diagram and tell you, if here this is your channel bed if here the depth was y1, then the depth of flow varies gradually. So this is y2. So what you will see that the distance x where the depth of flow varies is generally in kilometers in the case of gradually varied flow, right? Now, there are following assumptions which you have to, I think you should know basically, because if somehow it will ask you 2-3 statements are given and you are made to solve that which of the following statements are correct regarding the assumptions of gradually varied flow, I think you should be familiar with it, right? So now, the uniform flow formula such as Manning's or Chase's is used to evaluate the energy line slope. That is, you know the formula of Manning's 1 by n r to the power 2 by 3 s to the power 1 by 2 for Manning's velocity, and for Chase's it is c root over r s. So these formulas are used for calculating the energy line slope SF, right? Now, bottom slope of the channel, we assume that the channel bottom slope is very small. Channel is prismatic because right in the first, when we are dealing with the introduction chapter, we make it clear that in open channel flow, we will be focusing only on rigid boundary and prismatic channel only. And what is prismatic? Cross section shape, size and bed slope are constant throughout the channel section, right? So now, channel is prismatic, the energy correction factor alpha is unity. Fine, alpha value is 1, so it is unity. Basically, you can call it as kinetic energy correction factor also. After this, the pressure distribution which is acting, the pressure which is acting along the channel, that is your hydrostatic. So it is written that the pressure distribution is hydrostatic. Fine. Now, last one is the roughness coefficient is independent of the depth of flow and it is constant throughout the channel reach considered. That is, this roughness coefficient, that is Manning's NUT. It will not depend upon the depth of flow, whether it is changing or whatever is happening. It will remain constant throughout the channel length which is considered, right? So now, following are the assumptions, and on the basis of that, we derived the differential equation for gradually varied flow. First format you can write dy by dx is equal to S naught minus SF upon 1 minus Fr square, right? And in the place of Froude number, you can write q square t upon Ga cube. Basically, Froude number is root over q square t upon Ga cube, and Froude number square is q square t upon Ga cube. So you can write either in this format or in this format, anyone. Fine. Now, if you are substituting the values of Fr and you are taking SF common and substituting some values in terms of SF, fine, means you are substituting the values by replacing SF in terms of the depth of flow exclusively for wide rectangular channel, you will be getting this value of dy by dx. Now, two things which you should know. I have written here that it is a wide rectangular channel. So, when it is a wide rectangular channel, what will happen? Width will be very greater as compared to the depth of flow. So, what will happen? Hydraulic radius will be equal to the depth of flow, right? So, we can derive dy by dx by Manning's formula also and by Chase's formula also. So, by Manning's formula, dy by dx is equal to S naught 1 minus yn upon y to the power 10 by 3 upon 1 minus yc by y whole cube, right? What is yn? Yn is the normal depth, yc is the critical depth and y is the given depth, right? Similarly, you can derive it for Chase's formula also. By Chase's formula, what it is? dy by dx is equal to S naught 1 minus yn by y whole cube upon 1 minus yc by y whole cube. Fine. So, by Chase's formula also you can write the value of dy by dx and by Manning's formula also, right? Now, the main part, water surface profile. Fine. Water surface profile, what are the different types of water surface profiles? Basically, there are first of all 5 types of slopes which are considered. First one is your mild slope, second one is your steep, critical, horizontal and adverse. Total there are 5 different types of slope. Now, things which you should know about this is, first, what is NDL and what is CDL. NDL is your normal depth line, CDL is your critical depth line. Fine. Now, what does it stands for? The depth corresponding to NDL is your normal depth, while the depth corresponding to CDL is your critical depth. Right? This much is clear. Now, what happens is, basically you have 3 zones. Fine? You have 3 zones here, 1, 2, 3, 1, 2, 3. So, we assume that firstly there are 3 zones. So, for 5 slopes there should be 15 flow profiles. But actually it doesn't happen. You have 12 flow profiles. Why? I will tell you. First, let me define what is the zone. Let me name it as 1, 2, 3. Fine. What will happen is, any portion between NDL and top portion and NDL, or top portion and CDL, it is known as zone 1, that is top portion and NDL or top portion and CDL. This is zone 1. Fine. Don't look at the flow profiles now. Don't look at the flow profiles. Just see what I am telling you. Fine. Now, the portion between NDL and CDL or CDL and NDL is known as zone 2. Right? The portion between NDL and CDL or CDL and NDL is known as your zone 2. Now, what about zone 3? The portion between the bottom and CDL or bottom and NDL is known as your zone 3 profile. So, wherever you will see, you are getting here 3 flow profiles, 3 for mild slope, 3 for steep slope. But when you go for critical, you will see 2 flow profiles. Similarly, when you will go for horizontal, you will see 2 flow profiles, and same for adverse also. Why? I will tell you. Just one thing which you should remember before I will tell you further, that in the case of mild slope, your NDL is above CDL line, right? And in the case of steep slope, your critical depth line is above as compared to the normal depth line. Similarly, in the case of critical slope, your NDL and CDL are almost equal. They are almost equal, right? For horizontal case, you have only zone 2 and zone 3. You have CDL because there is no portion between NDL and top which is existing. That is why zone 1 for horizontal does not exist. Similarly, you can see for adverse, zone 1 does not exist for adverse slope also, right? This much is clear? Now, for the slope profiles, the names initial M, so it is M zone 1, M2, M3, zone 3, right? With the initial names, they have written it, alphabet, with the initial alphabet S1, S2, S3, horizontal H1, H2, S3, right? Now, how this flow profile is formed? We have to discuss that how this flow profile is formed. So now, for this flow profile, you have 2 slopes basically, S0 and SF. These are the 2 slopes. For S0, we use normal depth, and for SF, energy line slope, we use this Y depth of flow. So now, what happens in the case of your normal depth greater than given depth? What will happen? What all the permutation and combinations? You tell me. I will give you a question. Let me answer it, or you answer it by yourself. Fine. Now, what is happening? You have this mild slope, then you have a steep slope. You have a horizontal slope also, and you have an adverse slope also, which is moving like this. Fine. You can see here the slope here in the case of adverse is less than 0, or you can say is negative. Right? Now, what is happening? If your slope is slightly inclined, what will be the depth of flow? And if your slope is steep, what will be the depth of flow, or you can say there is a larger inclination, then what will be the depth of flow. I want the comparison. If your slope is slightly inclined or if it is inclined to a greater extent, what will be the depth of flow, whether it will increase directly proportional, inversely proportional. Come on, tell me fast, because without that I don't think that you will be able to draw flow profiles. You can mug it up. So shall I tell you? What is happening is, when your slope is slightly inclined, the depth of flow will be comparatively larger, while if you have a steeper slope, the flow will move. The depth of flow won't be that much as compared to the mild slope. In the case of steep slope, the depth will be less and it will move, right? So here also, if your S0 is greater, then what will happen? Your depth will be less, right? So there are some points which you should remember, because of which you will be able to draw the flow profiles, right? So if I am considering regarding the points, so some points are like this. If your S0 is greater, then your normal depth is less. Similarly, if your S0 is less than SF, Yn will be greater than Y. Fine? All these why I am telling, because these values when you will substitute here, you will get the answer what will be dy by dx. Fine? Now, as for now, I will be telling you only the important things. Similarly, when your S0 and SF are equal, your normal depth and given depth will be equal. Now, what you will do, if you have imagined or if you have noticed basically here, zone 1 and zone 3, for any case you take, for all the 5 slopes, you see wherever I have written 1 and wherever I have written 3, they are the rising profiles, whereas wherever 2 is there, you will see a drawdown is happening, fine, or you can say a falling profile is formed. Why? Whenever you substitute the values, you take any value y here and compare it with yn and yc, and you substitute it here, you will be see that in case of first and third zone, dy by dx is greater than 0, and while in the case of zone 2, dy by dx will be less than 0. So, just one thing I will tell you, whenever here I have written the important points, you can write it down later. When dy by dx is greater than 0, it is known as backwater curve, right? And when your dy by dx is less than 0, you get a drawdown curve. What was happening in the backwater curve? This. The depth of flow increases in the direction of flow. This is your backwater curve. And what happens in the case of drawdown curve? If this is your channel wind, the depth of flow decreases. Fine? So what you will see, that your zone 1 and zone 3 is always a condition of backwater curve, and zone 2 is the condition of your drawdown curve. So wherever you will see this only. Now, 2 points more basically. Now, what is happening if you want to know the flow profile at this particular instant? Fine, zoom it. If you want to draw it at this particular instant, what you will see, that the given depth y is almost equal to yn. So, when your depth y is almost equal to yn, then you will get the value of this dy by dx as 0. Similarly, if your given depth y is almost equal to yc, then this value of dy by dx will be infinity. So what does this give you a statement? It tells the water surface profile will touch NDL asymptotically since dy by dx is 0. And when dy by dx is infinity, what you are seeing, the water surface profile will touch CDL tangentially, right? So, excuse me, the water surface profile CDL will touch the water surface profile will touch CDL tangentially, and similarly the water surface profile will touch NDL asymptotically. Now, two more conditions. What are they? When y exists somewhere at infinity and y is almost here somewhere to 0. So, what happens? When y exists somewhere at infinity, your dy by dx value will be equal to only S0, and when your y is almost 0, then what will happen? I have already written it here. The surface profile meets the bed vertically if the depth of flow reduces to 0. When y is 0, dy by dx is infinity, and when your y was infinity, that is depth of flow exists somewhere at infinity, in that case you have dy by dx as S0. Fine. So, these things if you know, now there is nothing to know. Wherever you move, zone 1, zone 3, rising curve, it is rising. What is happening? NDL asymptotically, right. CDL tangentially, right. Here also CDL tangentially. So, any case you will see that only that zone 2 is a falling profile, zone 1, zone 3 is a rising profile, CDL tangentially, NDL asymptotically. Fine, this much is sufficient. Now, one thing which you should know is what is break in grade, because when I am telling you that this should be known to you regarding the mild slope, steep slope, what is the use basically in gate examination, that also I will tell you. If you will see break in grade, you would have heard when two different slopes are there, okay? They are known as break in grade. Like if I am taking a mild slope, and then a steep slope. So, this is a mild slope and this is a steep slope. Fine, a mild slope is there which is followed by a steep slope. So, what happens is, first I will tell you, you know that critical depth, let us suppose for rectangular channel section only you take it. This is, this formula you know, yc is equal to q square g to the power 1 by 3. You see that there is nowhere the condition of slope, there is no existence of slope, that is critical depth does not bother about the slope. Be it any slope, be it mild, steep, horizontal, I am not at all bothered. I will flow with my depth line. I am not at all interested with the type of slope. Fine. So, whenever you are drawing break in grade, first draw the CDL because it is constant throughout the channel section and it does not depend upon the slope. Fine. So, now first I will draw your critical depth line. Now, the reason I told you that you should remember mild slope is what is the condition positioning of NDL and CDL. In case of mild, NDL is above, and in the case of CDL, sorry steep, NDL is below CDL, right? Now, while you draw break in grade for the different types of slopes, find the flow profiles for basically different types of slopes in break in grade, you have to see one thing, you draw CDL and first draw CDL, then draw NDL, and then what will happen, a flow will start from NDL, it is an assumption and you have to follow it. A flow will start from NDL and it will try to meet NDL only. So, I do not know, you have to draw a flow profile, that is your main motive is flow should start from NDL and it should try to meet NDL. Fine. So, for my simplicity what I do is this break in grade I put dots here at this position. You without dots also you can solve, but I have this habit, and similarly I number this 1, 2, 3 so that I have that in mind that whenever I am drawing flow profiles I do not neglect the rules which are there, neglect the points. Fine. So, now if the flow starts from NDL, it will be asymptotically and it will touching the CDL, it will be 90 degree. Fine. Now, since it is a zone 2, so it should be falling profile followed. From this position, it is moving again to zone 2, it is touching NDL, it will touch it asymptotically. Here it was touching the CDL line, so it was tangential. Then it is moving to NDL, so it is touching it asymptotically. Zone 2 falling profile. Every rule followed. So this is your M2 S2, right? So in this manner you can draw the break-in grade provided you know the positioning of CDL and NDL and you follow the rules, right? Now one more thing is there about control section. What is control section? I will also give a brief idea for that. Control section is where a fixed relationship exists between the discharge and the depth of flow. It is known as your control section. For subcritical flow, control section is in the downstream direction. For supercritical flow, control section is in the upstream direction. Fine, this you should remember. So everything which we have covered here, just one thing which is remaining is your length of curve profile between the two sections. Now if I am taking, let us suppose this is a curve profile, this is to depth yi plus 1, this is yi, and I want to know the length which is existing. So here what is happening, I am taking any two sections, section 1 and section 2. So for knowing the flow profile, what is the formula? Delta x, that is x2 minus x1 is equal to E2 minus E1 upon S0 minus SF bar. And what is this SF bar? It is the average of the energy line slope at section 1 and at section 2. Fine, this much is clear. Just one thing I will tell you, in the GATE examination one question has already been asked previously. So what you do is, you calculate, you have been given depth at section 1 and at section 2. You calculate the average depth and then you find the average energy line slope. No, don't do that way. It's better and more precise and accurate if you calculate the energy line slope at section 1, similarly at section 2, and you then take an average, then you will get the average energy line slope. This approach is far better, accurate and precise, right? So I hope you are clear with the whole concepts which we discussed regarding the gradually varied flow. Now we will be moving to the rapidly varied flow. So now after gradually varied flow, we will be moving towards the rapidly varied flow. Fine. So we will start from the basic as we did earlier also. What is rapidly varied flow? The depth of flow changes suddenly over a small length of the channel, just opposite to that of your gradually varied flow. I have drawn this diagram also to explain, that is, if the depth was y1 initially, it moved to a depth of y2. But the distance in which the depth of flow changed is in meters, that is, within a small range of distance the change in depth occurred, right? So now, and what happened in gradually varied flow? The change in depth occurred over a large distance, that is, generally x is in kilometers. Fine. Now, what is an example of rapidly varied flow? Hydraulic jump is an example of rapidly varied flow. So now, what happens in the case of hydraulic jump? Whenever your flow occurs from supercritical region to subcritical region, there is a formation of hydraulic jump. Because you would have seen in case when we were dealing gradually varied flow, the M3 profiles, whenever it is formed. So what will happen? When M3 profile occurs, after that a hydraulic jump occurs and it reaches to normal depth line, it happens, right? So now, here y1 depth was there, where your Froude number is greater than 1, that is, it is supercritical. Here your depth y2 is there, Froude number is less than 1, that is subcritical. So first I have written, when the flow condition changes from supercritical to subcritical, the result is an abrupt rise of water, that is energy dissipation, or you can say dissipation of energy takes place. So this way we basically draw your hydraulic jump, right? So here you can see two depths, one is your y1, another one is your y2. So what is this y1 and y2? These y1 and y2 are your sequent depth, or you can tell it as conjugate depth. In energy depth relationship, we were having same specific energy, so it was alternate depth. Here we have the same specific force, because of which it has sequent depth or conjugate depth, right? Now, what is specific force? That also we need to study. So, specific force F is equal to Q square upon Ga plus Az bar. And what is this Z bar? This is depth of centroid of area, name it A, because here A is there, from the free surface. right? Like if you are taking a rectangular channel section, it will be y by 2, that is half the depth of flow. For triangular channel section, it will be 1 by 3 of the depth of flow, right? So now, if you have been given two sections, section 1 and section 2 of any channel, then you know that the pressure distribution is hydrostatic. Fine, P1 and P2 are the pressure forces which are acting. So what will happen? I have already told you that in the case of rapidly varied flow, what is happening? Your specific force is constant. So what we have written? Q square upon A1G plus A1Z bar is equal to Q square upon A2G plus A2Z2 bar, right? Now what is this Z1 bar? This is depth of centroid of area A1 from free surface. And similarly, what is Z2 bar? That is depth of centroid of area A2, name it this area to be A2 from the free surface, right? So now, what is happening? Now I want a particular format of expression for calculating the numericals. This is valid for any shape, triangular, trapezoidal, rectangular, any shape. But now, if I find the expression specifically for rectangular, I will substitute the area of rectangular, depth of centroid, everything for rectangular, I will get this result. What is this? YCQ is equal to Y1, Y2, Y1 plus Y2, where Y1 is your supercritical depth, Y2 is your subcritical depth, right? Now, this expression can be written in the format of 2q square by g, y1, y2, y1 plus y2. How come? You know that ycq is equal to q square by g. So, in place of yc cube, I can write q square by g and this 2 will come here. So, you will get 2q square by g is equal to y1, y2, y1 plus y2, right. This will be your expression format for that, right. So, this way also you can write the expression. If you are given critical depth, so you use this formula. If you are given discharge per unit width, you can use this formula. Now, there is this Ballinger's momentum equation which has been a vital role to play, because many a time question has been asked from this formula. But this formula you should remember that this is applicable for horizontal frictionless rectangular channel only, right. So, what you can write? Y2 by Y1 is equal to 1 by 2 minus 1 plus root over 1 plus 8 FR1 square. Whatever in this in the denominator, Froude number square of that. If your 1 at section 1 is there in the denominator, so section 1 square. Similarly, you can write it in the other way round also, that is y1 by y2 is equal to 1 by 2 minus 1 plus root over 1 plus 8 FR2 square, right. If there is a formation of hydraulic jump, obviously there will be a power loss also, right. So, power loss of hydraulic jump is given by gamma q delta E, where gamma you can write it in rho g also, q is your discharge and delta E is your energy loss, right. So, how can you write energy loss? Either you can write EL or you can write delta E, and what it is? It is y2 minus y1 whole cube upon 4 y1 y2. This expression you should remember at least, fine. Or you in the form of velocity you can write v1 minus v2 whole cube upon 2g v1 plus v2. In any of the way you can calculate the energy loss if you are given the depth or if you are given the velocity, right. Now, what is the height of jump? How can you calculate the height of jump? Like if it is moving from y1 to y2, I have already drawn the diagram. So, height of jump will be y2 minus y1, because you know whenever there is a formation of hydraulic jump, your subcritical depth will be greater than your supercritical depth, that is your y2 will be greater than your y1. So, I have written here height of jump is equal to y2 minus y1. Similarly, we can calculate the length of jump. This is 6.9 y2 minus y1. Now, how this expression came based on experimental studies? Generally, you get this length of jump is equal to 6.9 y2 minus y1. Fine. So, we talked regarding the power loss, energy loss, height of jump, length of jump. But we should know what is the location of jump also, right? So, for location of jump, you have this yt. This yt, that is the tail water depth has a very important or significant role to play, because this helps in classifying the location of the jump. Fine. So, what will happen in the case of free hydraulic jump, your tail water depth is equal to the depth at section 2. In case of free repelled jump, your tail water depth will be less than y2. And the last one is your submerged jump or drowned jump. In that case, your tail water depth is greater than your depth at section 2, that is yt is greater than y2, right. So, you can calculate the submergence factor also. Submergence factor is yt minus y2 upon y2. So, in this way you can calculate the submergence factor also. So, here we talked regarding the location of jump. Last is the type of jump. Although this many things are not important, I will tell you what are the things which are important, but still. Now, what can happen is, let me tell you one thing, they can give you the different parameters and they will give you 4 options out of these 5 jumps. You have to tell which type of jump it is. So, you have to calculate the Froude number and then you will be able to classify the type of jump, first thing. Next thing what they can give you is, they can give you these conditions and they can ask you to match the following with the given type of jump, or the Froude number they are giving and they can ask you to match it with the type of jump, or even they can give you the different type of figure and they can ask you to match it with the type of jump. Anywhere around they can ask you the questions, right. So, basically this is Froude number of the incoming flow, that is Froude number of supercritical section, right. That is why I have everywhere written FR1 for that purpose only, right. So, now we will start. We have 5 undular, weak, oscillating, steady and strong jump, right. So, first we will move from the undular jump. Undular jump occurs when the Froude number is 1 to 1.7. If it is in this range, then there is a formation of undular jump. This EL by E1 which is written here, this is your relative energy loss, which is almost 0, it is 0 point something or it is there. So, we almost assume it to be 0 in the case of your undular jumps. Now, what happens in the undular jumps? There are undulations, water surface is undulating, you can see there is an undulations and small ripples are formed on the surface, right. This is for your undular jump, and this EL by E1 is known as relative energy loss. Fine, I am telling you, I have not written it here. Now, second one is your weak jump. Here you can classify when your Froude number is 1.7 to 2.5, right. Relative energy loss varies from 5 to 18%. The thing it is called as weak jump because small amount of energy is dissipated. That is why it is a weak jump, because whenever you want to say about jump, there should be dissipation of energy should be more, fine. So, what you can say, the velocity throughout is fairly uniform, almost uniform, but a small amount of energy is dissipated in case of your weak jump. Fine, we want that basically relative energy loss should be more so that the randomness could be reduced, right. Now, third one is your oscillating jump. This you would be getting an idea because you would have seen the oscillations of pendulum clock to and fro, back and forth. So, similar thing will be happening here also, right. First move to the Froude number, it is from 2.5 to 4.5. Relative energy loss is considerably greater as compared to your weak jump. It is how much? 18 to 45%. And here the entering jet of water oscillates back and forth, you can see it here only, back and forth from bottom to surface and then it goes back again. In which case? In the case of your oscillating jump, right. Now, fourth one is your steady jump. What happens in steady jump? Your Froude number is varying from 4.5 to 9. Relative energy loss is 45 to 70%. In the case of steady jump, the jump formed is well stabilized. The reason, because of this reason only we prefer steady jump. Like if somebody asks you out of this 5 types of jumps, which jump is preferred? If you want to construct artificially an hydraulic jump, for what conditions you will be designing? So, generally we design it for steady jump condition, right. So, now The jump formed is well stabilized in the case of your steady jump. Last one is your strong jump. This strong jump you also call it as choppy jump, CHOPPY, choppy jump also. This exists when your Froude number is greater than 9, your relative energy loss is almost 70%, greater than 70%, and a rough surface you can say it prevails, the rough surface prevails, which continues downstream for a larger distance, or you can say for a longer distance. Fine. So, this will be a case of your strong or choppy jump. One thing which I will tell you is this percentage of relative energy loss may vary from book to book, but the variation is almost 5 to 10%, not more than that. Generally within this range only there is a classification of the different types of jump, almost in this range, right. So, I hope with the names, that is steady, strong or oscillating, you should give an idea that what is the type of jump. Like if they give you a figure and they will ask you to match the following, I hope you will be able to do it. Similarly, you should be thorough with the Froude number, so that if the data is given you can calculate and classify the type of jump, right. So, this portion of rapidly varied flow which talks regarding the various types of numericals which can be asked based on the given formulas we have discussed. Now, lastly we will be moving to the surges part. So, now this is the unsteady flow surges, the last topic of our open channel flow which we are discussing, right. So, we will start from the introduction part, from the definition as usual. What is a surge? A surge is a moving wave front which brings about an abrupt change in the depth of flow. That is, it is moving, basically it is called as a moving hydraulic jump also, because whenever there is a formation of surge, there is an abrupt change, sudden change in the depth of flow. Now, if there is a sudden change in the depth of flow, what will happen? Change can either be increase the flow depth, or it can decrease the flow depth. So, surge which produces an increase in flow depth is known as your positive surge, while surge which produces decrease in flow depth is known as your negative surge. Now comes the question, when is your positive surge formed and when is your negative surge formed? So, we will discuss that also. Whenever you close the gate suddenly, be it sluice gate, if you are closing it suddenly, now this gate, it is the initial position and you are closing it suddenly, what will happen? The flow depth which is there in the upstream will increase, because the amount of water which was going through this gate, you are closing the gate suddenly, and similarly what is happening? The flow depth in the downstream direction is decreasing. I have marked it here, right. So, what is happening? The flow depth is decreasing. Now, similarly, if you see when the gate is opened, what is happening? Your gate is opening. So, large amount of water from the upstream is moving to the downstream side. That is why I have marked it here, that a positive surge is formed, because what is happening when you are lifting the gate, large amount of water moves to the downstream direction, which leads to increase in flow depth. So, it will be a positive surge. Similarly, here since the gate is closed, there is a formation of negative surge in the downstream direction. So, what you saw, when the gate is closed, you have positive surge upstream, negative surge downstream. When the gate is opened, you have negative surge upstream and positive surge downstream. So, based on this, I have first put the heading of positive surge and negative surge, and then you have 4 types. So, first is your type A, positive surge advancing downstream, type B, positive surge advancing upstream. Similarly, for negative surge, you have type C, retreating downstream, you have type D, retreating upstream, right. So, how this diagram is drawn, just this I have marked. Take this portion of positive surge for now. Draw this portion. This is the green one, is the final which came when you opened the gate. So, what was happening? This was the final portion and then it met the initial portion of the water. Similarly, you can draw for anything, like if I want to draw it for this positive surge advancing upstream, that is for type B. What I can see, that this is the flow pattern. This is Y1, V1, Y2. This is the flow pattern, right? So you can just round it off, you can see the pattern exactly similar. See, this is the only thing which I have drawn. And what about the velocity VW? VW is the velocity of wave, or you can say it as velocity of surge wave, right? Now, since I am telling that it is moving upstream, that means VW is moving upstream, right? And now if you can see that retreating downstream. So this VW, velocity of wave, is moving downstream. Here also you can see upstream, so VW is moving upstream, right? So now we have to get an expression for calculating VW. So the expression of VW is V1 Y1 minus V2 Y2 upon Y1 minus Y2. This is the expression for calculating the velocity of wave, first thing. Now, the thing which is important and questions have been asked previously in GATE is celerity. What is celerity? Celerity is defined as the velocity of wave relative to the velocity of flow, or you can say it relative to the water velocity. Velocity of water also you can say, because the water is there here. Like velocity of flow, if you are talking about what is the liquid which is flowing, it is obviously water. So now this celerity is first of all denoted by C, and this is given by expression root over G by 2, Y2 by Y1, Y1 plus Y2. Fine. Now if you want that this expression should be shortened out by expanding and assuming it, you will get C is equal to root over G Y1, where this equation is known as Lagrange celerity equation, right? So you can calculate the value of celerity. Now, if in the question they ask you to calculate the velocity of wave VW, they give you the V1 velocity, they give you celerity. So first you have to check whether it is advancing downstream, upstream, positive surge, negative surge, that you have to check. They will give you some hints with the help of which you can check it. Now, after which you should know that what is the celerity in all these cases. Generally, with the help of derivation, you can derive that velocity of wave with respect to water, this is your celerity, is equal to velocity of wave with respect to ground plus velocity of ground with respect to water. But actually, we are not interested in the derivation part now, as for now. So I have written in the celerity, which will be varying. For advancing downstream, it is VW minus V1. Positive surge advancing upstream, it is VW plus V1. Similarly, for retreating downstream, it is VW minus V1, and for retreating upstream, it is VW plus V1. So you can see the celerity values with respect to velocity of wave and with respect to V1 is different for the different cases, right? So celerity is something, at least remember this formula and have this concepts being cleared. VW, V1, Y1 minus V2, Y2 upon Y1 minus Y2, that is a simple formula. So at least get your this concepts clear, that what happens when it is advancing downstream, what happens advancing upstream. I already told you when it happens, so you don't need to draw this diagram. If you know this when it is formed, you can draw it by yourself. There is nothing much rocket science in it, right? So now we have completed all the things which are important and which are helpful, be it in conceptual form or be it in expression form, which is helpful for solving your gate numericals. Although it took a time, it should be 30-40 minutes, but it took time because I don't want to leave anything. I wanted to cover be it subcritical, supercritical, hump contraction, hump formation of hump case, or be it your width contraction. I wanted to cover all this, fine. So I want that you should go through it, fine, and I hope you enjoyed this whole series of open channel flow, the whole chapters which we discussed thoroughly, the important concepts regarding it. So please keep practicing, keep learning. Thank you.